The points A, B, and C have the position vectors shown. Show that B lies on AC. So I'm going to go through this first of all with the vector method and then an alternative. Let's find out what AC is as a vector. So this is OA, OB, and OC. So if I've got a vector and I'm going from O to A, and another vector and I'm going from O to C, if I want to go from A to C, then it'll be minus OA plus OC, or OC minus OA. It's always the second minus the first, I've just derived it along the way. That will give me minus 1 minus minus 4, so 3, and then 12 minus 3 to give 9. We want to show that B lies on this line, so let's find out AB. We could also find out BC, but let's go with AB. For similar reasons, that will be OB minus OA, which is minus 3 minus minus 4, so 1, and then 6 minus 3, 3. And comparing them, we can see that 3AB is going to be 3, 9. So 3AB is equal to AC. Therefore, well, they're parallel vectors and they both start at A. So AB and AC parallel and both go through A. So B must lie on AC. That's enough to show it. Okay, now here's a completely different approach. If you're not a fan of vectors, you might like this. We're just going to use the equation of a straight line. We're going to treat these as coordinates. So we had A as minus 4, 3. B is minus 3, 6. It's not particularly to scale, but just a little sketch of what's going on. And then C is minus 1, 12. Okay, it's going to be somewhere up here. So I'm going to find out the equation of AC. Let's get the gradient. M is going to be y2 minus y1, so 12 minus 3, over x2 minus x1, minus 1 minus minus 4. 9 over 3 is going to be 3. Y minus y1 is equal to mx minus x1, so I'll substitute in, say, the coordinate for A, so y minus 3 is going to equal 3x minus minus 4, so x plus 4. Y equals 3x plus 12, and then plus another 3, so 3x plus 15. And that's our equation of AC. So when x equals minus 3, that's my coordinate for B, y is going to equal minus 9 plus 15 equals 6. And therefore, B lies on AC. Completely different to a vector approach. It works quite well. You could alternatively work out the gradient. This is a fourth method. It's a fourth method because we could have dealt with, instead of doing AB, we could have done BC over here. So, okay, they're very similar. And this fourth method is very similar to this one. We could work out the gradient of AB, show that it's also equal to 3, and therefore it must be, because both of them go through A and we're going along the same gradient, then we must go through B to get to C. That's another way to do this question. For part 2, find the ratio AB to BC. Well, we've worked out the vector AB, and we can find the magnitude using Pythagoras. You don't actually need the vector either. You can just see we're going 1 along and 3 up. But it's going to be 1 squared plus 3 squared square rooted, so square root of 10. And then for BC, well, actually, like I said, I'm not going to find the vector. I can just see that I'm going 2 along now. And from 6 to 12, so 6 up. So it's going to be 2 squared plus 6 squared, which is root 40, which is 2 root 10. And therefore, AB to BC is going to be root 10 to 2 root 10, divide through by root 10, giving us 1 to 2. Moving on, we're given a diagram with x plus y equals 6 drawn on it, and the point P24 that lies on the line. Distinct point Q also lies on this line and is such that OQ equals OP, where O is the origin. So let's get this vector drawn. So this is the magnitude. Therefore, I'm doing 4 squared plus 2 squared. Get the magnitude, square rooted, which is going to give root 20. So I'm looking for somewhere on the line that's also that same distance away. Well, actually, I can just go 4 along and 2 up instead. That will work out. Because what we have here is essentially a circle. Like that, those will be all the points that are root 20 away from O. So it's just going to hit at that other point there. So Q is actually 4, 2. Now, actually, it doesn't ask us for that. It asks us for the magnitude and direction of the vector PQ. So this one here. And I can see that I'm going 2 along and 2 down. So 2 minus 2. And therefore, sorry, I know I'm running out of space here, but PQ, the magnitude is going to be 2 squared plus minus 2 squared. That's 8 square rooted. So I'm going to get root 8 or 2 root 2. That's my magnitude. And then the direction, well, this is actually a right-angled triangle isosceles because it's 6 and 6 in length. So this angle here is 45 degrees, which means if I draw a line here, then this is 45 degrees below the horizontal. Now I wrote below the horizontal, but I don't think that's enough information because I'm not saying if it's going to the left or the right. So what we should actually do, you could use a bearing, you'd get away with that, but there's a standard way for saying the direction, and that is how much you are turning clockwise from the x-axis. So we're actually, because we're going down, we're actually going all the way around here, 315 degrees. So direction, you could alternatively say minus 45 degrees, that would be accepted. But go with that rather than 45 degrees below the x-axis or below the horizontal. All right, the very last part, C, I've decided to use a fresh diagram for this. I think it'll just make things a little bit easier. We're told that the point R is such that PR is perpendicular to OP and PR is a half of OP. Let me deal with that OP bit. I think I already talked about it being root 20. So OP was 4 squared plus 2 squared root 20, which we could write as 2 root 5. So that means that the magnitude of PR is just going to be root 5, which, by the way, is 2 squared plus 1 squared. So that might be useful. Let's draw the perpendicular line. So the points are such that PR is perpendicular to OP. Now for this, I can see the gradient I'm going along 2 and up 2. So up 4, sorry. So the gradient is 2. So I need a gradient of minus a half to create a perpendicular line. therefore I'm going to be going in this direction here. So R could be, if I put R here, for example, then PR would be perpendicular to OP anywhere along this line. I just need it. So R is now, so PR is root 5, i.e. 2 squared plus 1 squared. So I just need to go along 2 and down 1, and that is going to be a position that would work. This satisfies PR being perpendicular to OP and the magnitude of PR being root 5, which is a half of OP. So positions, we could have R as 4, 3. Alternatively, I could go up 1 and back 2. That would also be root 5 away. So right here, which would give me R as 0, 5. Okay, that bit's a bit tricky. I think it really helps to start afresh on a new diagram to see what's going on. Well done.